Hello. In this video we're going to be talking about MergeSort, a very popular divide and conquer style algorithm. We're going to look at the algorithm itself and decipher the sort portion of the MergeSort algorithm. So let's see what's coming up. We're going to be talking about MergeSort, and as you can see in terms of time complexity, it is one of the most efficient sorting algorithms, enjoying very good time complexity in the worst and average cases. MergeSort, as mentioned, is efficient, one of the most efficient sorting algorithms, big O and log n, typically offering performance only slightly below that of quicksort. It is a stable sort, and when sorting lists, MergeSort requires additional scratch space proportional to the size of the input array. It is also relatively easy to code. MergeSort exhibits a classic divide and conquer strategy. First we divide an n-element list or sequence into two sorted subsequences of n over 2 elements, so about half, and conquer, sort the two subsequences recursively using MergeSort. Finally combine, merge the two sorted subsequences to produce the sorted answer. Here we are assuming a base case of 1. In other words, a list that consists of one element is considered to be already sorted. Here's a diagram that explains MergeSort. We start with an unsorted list, and we start with a divide stage. We divide in half, and so on, until we reach our base case of lists of one element each. We leave the divide stage and then enter the merge or conquer stage. When merging, we don't simply put the two sides together. We have to actually conquer or solve the problem. In other words, putting them together sorted. In this case, in the first example, for instance, 7 before 14, 3 before 12, and so on. We keep doing this, we keep merging, until we merge the one half with the other half, and finally arrive at our final solution, a completely sorted list. Here's how it looks like dividing and conquering the entire algorithm in a diagram format. This is the MergeSort algorithm. We first calculate the mid, then we recursively merge the first half, recursively merge the second half, and the final merge puts the two sorted halves together. We will investigate the merge algorithm here in a little bit. So here's merge. If I have two subsequences, A and B, that are already sorted, if A is empty, I can append what's left in B, the other list, to C, my result. If B is empty, in other words, the opposite case, I can append what's left in A to C, the result. However, if the first item in A is less than the first item in B, I'm going to append the first item in A to C, the result, and then call merge on the rest of A, B, and C. Else, where the first item in B is smaller, append the first item in B to C, and then merge A, the rest of B, and C. Why are we talking about the first element? Let's remind ourselves of the problem. Given two sequences A and B, sorted in non-decreasing order, merge them to create one sorted sequence, C. In which location does the smallest item exist in each of these lists A and B, remembering that they're sorted? Well, at the beginning or at the front. So if I wanted to find out the smallest item, I just have to compare the smallest item in A and the smallest item in B and choose which of those two elements is the smallest, and then continue picking out the next smallest and the next smallest in a similar way. So what two things are we comparing at any given time? Basically the head or the start of each of these lists. Let's perform MergeSort on an unsorted list of 8 elements. So first we divide. So we take 8, 3, 2, 9, 7, 1, 5, 4 and divide it into two lists of 4. Then divide two lists of 4 into 4 lists of 2. Finally, we divide into single elements. Now we can merge. 8 and 3 we merge such that it's 3 and 8. 2 and 9 we merge 2 and 9. 7 and 1, we merge 1 and 7. And 5 and 4, we merge to 4 and 5. Now we take 3 and 8 and 2 and 9 and merge those together. So 2, 3, 8 and 9. And then we take 1, 7 and 4, 5 and merge those together. 1, 4, 5, 7. Finally, we merge the last two lists of 4 together into one final result, which is sorted. But how exactly are we doing this merge? We'll talk about that in just a moment. Here's an example when we're doing the same thing, however, using an odd number of elements. As you can see, it can be done. Pause the video to see how it's done. So let's examine merge using a very small example. So let's say we have two lists A and B. A is 3 and 8, and B is 2 and 9. See, the result is currently empty. The red elements are at the head of the list, and underlined is the smallest element. The green is the rest of the items in the list, and C is the growing sorted list. So I look at the head of A and B, in other words 3 and 2, realizing that 2 is smaller, therefore 2 is the one that's underlined. I place that element into my result, 2. I can think of this as having pointers to the head of the list. So let me move the pointer of list B over by 1, because I've moved 2 into my result. So now the head of each of the lists is 3 and 9. 3 being smaller, I move 3 into C, the result. Then 8 and 9, 8 is smaller, I move 8 into the result list C. And then this is where we come to the algorithm that says, if one of the lists is empty, move the rest of the other list into the result. In this case, I have only one item in list B left, so I just move that to C. As you notice, C now holds the final result, sorted 2, 3, 8, and 9. We are done at this point. What about duplicates, you might ask? Well, certainly we can handle duplicates by making a small change in our algorithm. We can say else if the first item in A is less than or equal to the first item in B, and then continue the algorithm in the exact same way.